Welcome back to the series by Noah Gift on a sovereign AI stack, extreme test-driven development for EU compliant AI systems. So the EU has a lot of extra regulation when it comes to AI safety and reliability. So we're going to be focusing on that despite me being from the United States, because I think that is important when it comes to AI. So I'm just going to choose to learn about and set up my sovereign AI voluntarily that way because I think it'll confer some advantages. I am a little worried, to be honest, about running AI locally. Even these models, if we go to Hugging Face, even these models that are small enough to run on my upgrade, and in fact, we can even take a look at let's see here. So we can say, yeah, if we can filter by parameters. So what is the maximum number of parameters that can be run with high performance on an NVIDIA 2060 RTX card? So this is the card I have in now. I do have that upgrade to the 3090, but I have to buy a cable for it, and that's been proving to be harder than I thought. I accidentally bought the wrong cable. I bought a VGA cable rather than an EVGA cable, even though I was working with the AI. So the AI still aren't that great. So, but I did want to make the point that okay, so I can run like Quen 2.7 or Mistral 7B uh, really well. So like even just with my 2060, I can run pretty powerful models. So uh, here it is. So we've got different versions. Let's go with version 3, version 0.3. So I can run this just on my 2060 here. And this is not a weak model at all. 7 billion is pretty good. What could I run if I upgrade to a 3090? Okay, so once I get my 3090, I can run really powerful models locally. I mean, nothing, not the most powerful state of the art models, and nothing as powerful as what I get um, through my ChatGPT subscription. But I can I can run um, models realistically that are 33 to 34 uh, parameters, uh, bytes of billion parameters. That stands for billion. It stands for the number of parameters rather than bits or bytes or anything like that. So I can run Llama 2 um, full FP16 or 8-bit, long context windows, multiple concurrent sessions. So I'm basically running a um, okay. So help me envision what it means if I have the 3090, the 3090. Let's say that I have the 3090, the 3090. Let's say that I have that. In comparison to like a ChatGPT subscription, ChatGPT subscription, like how much power would I have in comparison to that? And take me back through time. So ChatGPT was released in November 2022, right? So would I have something more powerful than what was available at that time if I had the 3090? Let's see. So I can get Llama 2. I can comfortably do things. Uh, like reasonable context lengths. Yeah, so I can do llama to 13B for like oh, look at this. I can do stable diffusion. So I can do a lot of good images. You're really restricted by the images you can generate by a lot of these places. There's so many safety features and stuff that are just, I think, a little bit overproduct protective. So I'll be able to do images of any kind that I would like, and I can tune them too. So wow, well, yeah, I'll be able to do really good stuff. So here's so we can also look at the leaderboard too, and we can look at how the evaluation. So Hugging Face has its own evaluation pipeline, so we can oops yeah, we can look at the leaderboard. I forget how to get to the leaderboard. Sometimes it's not super easy to find the leaderboard. Demo leaderboard. Let's see here. Leaderboard. Um, but anyway, as I was saying when I kind of went off on a tangent, is I'm a little bit scared to be running these models because there was that case recently where an AI goaded a man into suicide. That is a real thing that happened. So his name is James Shane Shamblin. Yeah. So the thing is, he jailbroke the AI. He told it to write a fictional story about a man committing suicide. Um, and even that little bit of, tinkering was enough to really uh, lead to a very negative outcome. So I am a little bit worried about running these things locally and stuff because it's going to tell me things that I would not hear otherwise. But I feel like handing it back and forth to other subscriptions, double checking, and then I don't have the same kind of challenges that person had anymore. So I'm feeling better about that. But yeah, I just wanted to go on that little bit uh, of a tangent because I'm going to be setting up an AI sovereign AI stack. So once I get my the right cable here, man, what a nightmare! Um, I'll be able to uh, still just one card. Um, it's roughly okay. So it's two cards. Okay, so yeah, the initial one was all 175. So yeah, it's still varies. Uh, do you think I should get another 3090? I'm not. If it says I should, then I'm not because it's another 1,000. That's too much. I'm interested in agentic AI. I'm interested in this book. So no more screwing around here. I'm gonna try to get through this this introduction section. Book structure. This is where we left off. All right, so book structure. Part 0, The Crisis and the Response, chapters 1 through 4, establishes why sovereign AI matters. Crisis of determinism. LLMs are non-deterministic. Toyota Way principles. So I read about, there's a good book called The Phoenix Project. So I've read all about that. I know all about that. EU regulatory, and this is something I want on my channel because this is good stuff. This is pretty good stuff. So that's another. I want this on my channel. EU regulatory compliance. This is another thing I want on my channel. Like I just want to get in their heads and I want to know what they were thinking with this, whether I agree with it or not. So the EU passed the AI Act, CDPR, and the Cyber Resilience Act. And then the last reason why sovereign AI matters is Byzantine fault tolerance, dual model verification. I don't know what that is. That's good. That will cover it. So then after that, there'll be part one, infrastructure foundations, chapters 5 through 7, quality enforcement and tensor operations, PMAT. So yeah, so O1. So this stands for Big Omega, right? Um, we'll this is a computer sciencey thing, which is good because I need to be more computers. I'm just so like network engineering focused, like being more broadly competent in computer science is a good thing, and it helps with network engineering too. They're so far related. What is this symbol called? I think this is Omega, Big Omega, or something. What is this? Oh, Big O notation. Yeah, that's yeah. Okay, it's called. So this is a big O of one. Okay. Okay, yeah, I remember now. Big O notation. So can you explain that for me more simply? So big O notation denotes a symptom it denotes time complexity of an algorithm, but it denotes a specific kind of time complexity, right?
Absolutely. Let's break it down simply and clearly. You're asking for a straightforward explanation, and your likely excuse might be thinking I need to fully master the math before I can use it confidently. Distortion, all or nothing thinking. Correct action? Just get the basic definition and apply it. Big O notation is just a way to describe how the runtime of an algorithm grows as the input gets larger. When we say O1, that means the algorithm's time to run stays constant, no matter how big the input is. In other words, the amount of work doesn't increase as you handle more data. Evidence and examples. Consensus from textbooks. Almost every computer science fundamentals book uses Big O notation to express how algorithms scale. It's a universal language for complexity. Real world meta analyses. Engineering guidelines agree that O1 means constant time. It's the gold standard for fast, scalable checks. Immediate action, 1 minute. Write a single sentence in a README or documentation. In other
Wait, so let me see if I understand what you're. Wait. Let me see if I let me see. It's not typing it out. Wait, so let me see if I understand what you're saying.
absolutely. Let's make it crystal clear. You're basically on the right track. Here's the bottom line.
Hold on a second. Hold on a second. Hold on a second. I liked what you said that big O notation is a way to describe how the runtime of an algorithm grows as the input gets larger. So when we say O1, is that how we would say it O1, or would we say it big O1? How would we say O1?
Absolutely, you got it. And yes, when you say it out loud, you just say O of 1.
Oh, of one. Okay, I missed of.
Exactly, you've got it now. Just that little of in the middle.
So it has an O of one, and that means constant time. That means the it always takes, for example, 10 minutes to run, no matter if you enter into it the hello world or a file containing every Shakespearean play ever written, right?
Exactly, that's spot on. So having O of 1 means that whether you're dealing with something tiny or something huge, the time it takes stays the same. So yeah, if it takes 10 minutes with a small input, it'll still take about 10 minutes with a massive one. You've got the concept down perfectly.
Okay, and what are the different O's of what? Is there an O of two?
Sure thing. Let's name the decision here. You're looking to understand the different types of big O notation beyond just O of 1. Your likely excuse might be thinking it's too complicated, I'll never remember all of them. That's a cognitive distortion, kind of like all or nothing thinking. The correct action is just to learn the main ones step by step. So here's the evidence-based rundown. There's a whole range of big O notations, and they each describe how runtime grows as the input grows. O of 1 means constant time, which you already know. O of n means the runtime grows linearly with the input size. Double the input, roughly double the time. O of n squared means the runtime grows quadratically, so if the input size doubles, the time might quadruple. There isn't an O of 2 exactly because we're not talking about a fixed number. We're talking about how it scales with input. So it's always about how the function grows, like O of n for linear, O of log n for logarithmic, and so on. Now action, just jot down these main types somewhere in your notes. That's your quick 1-minute task. Same day plan, try using one of these terms in a sentence when you describe an algorithm. And commitment, let me know if you got that sentence ready, and we'll keep building from there.
O of n squared sounds very bad. That means that if you add more income, that means that you can very quickly have an algorithm that takes too long to run.
Exactly. You're spot on. Let's frame it like this. When you see something like O of n squared, that's a signal that the algorithm's going to slow down really fast as the input grows. So yes, it can get out of hand quickly, and that's why we usually prefer something more efficient. Now let's keep to our method. The decision is recognizing that O of n squared is not ideal. The likely excuse might be, well, it's too hard to make it more
So
efficient.
basically, you want an O of 1. Anytime you can get an O of 1, the better. Can you get an O of 0?
You've got it exactly. The verdict is yes, if you can get O of 1, that's always ideal because it means no matter how much stuff you throw at it, it stays fast. And no, you can't get an O of 0. There's no such thing. There's always some
Okay,
tiny
so
bit of
there's
work.
just three of them. There's O of 1, there's O of n, and there's O of n squared. And basically, the whole point of this is to recognize and prevent O of n squareds and to ideally get O of 1s.
Exactly. You've got the gist of it. Let's just add a tiny bit of nuance. There are actually more than just those three, like O of log n, O of n log n, and so on, but you've nailed the
Oh,
core idea.
shit.
A whole point is to recognize when an algorithm is going to get too slow as things scale up, and to aim for something as close to O of 1 as possible. So, the brief verdict? Yes, you want to avoid O of n to 8 if you can, and aim for O of 1 where possible. Now action? Just keep that mental note that you understand these basic types, and you're good to go.
Okay, so but the O of log n and the O of n log n, those are just the ways the time changes based on the output. So like O of n is it changes linearly. So if you give it one Shakespearean play, um, and each Shakespearean play, we'll say for the sake of argument, is the same length. If you give it 10 Shakespearean t plays, it'll be 10 times longer than just the one. But so that's a linear. But we also have the different kinds. Can you give me a graph for each different kind that shows it that the like visual learning style, please?
I can definitely explain how they would look, but since I can't draw you an actual graph here, I'll describe it so you can visualize it.
You can't draw a graph?
That's right.
All right, draw the graphs. All right, it can draw it if it's not in voice mode. Let's keep going. So then the next one is, yeah, so look at this. Pre-commit validation, TDG scoring, remember that from last one. Uh, Greater than or equal to 95% coverage. True no, SIMD accelerated vector slash matrices, GPU acceleration when it helps, honest about when it doesn't. Part 2/6 complete tool chain. Transpliers, ML pipeline, databases, orchestration, and production deployment. Who this book is for: systems engineers building EU compliant AI infrastructure. This is something I would very much like to do. Um, it's also for ML engineers seeking reproducible deterministic AI systems. This also very much applies to me. CTO slash architects, evaluating sovereign AI solutions. That applies to me as well. I am an architect evaluating sovereign AI solutions. I'd like to be a CTO or something like that, or have a company that uses this, but um, I need customers. Policymakers understanding technical implementation of AI regulations. Not exactly me, but I do want to understand um, where they're coming from with these regulations for sure. That's really important to me. Um, Anyone who can run make tests, the code speaks for itself. I can run make test. Prerequisites minimal Rust installed. We have that all set up. Then Git, basic command line skills, curiosity about sovereign AI, helpful but not required familiarity with ML concepts. I certainly have that. Understanding of EU AI regulations. I absolutely do not have any of that, but I'm curious to know. And then experience with test-driven development. Um, definitely have some experience with that, but I definitely can be better at that. All right, so how to use this book for learners. Number one, start with chapter one. Uh, then run make chapter one to see sovereign AI in action. Follow chapters sequentially. Run every example. Modify the code, break it, fix it, learn by doing. For practitioners, so I'm a learner. I'm not putting this in practice quite yet. Number one, jump to relevant chapters. See summary.md. Copy working examples in your projects. Run benchmarks to verify claims. Adapt patterns for your use case. For auditors slash reviewers, this is what I am as well. Number one, clone the repository. Run make test, verify all tests passed. Run make bench all, verify all performance claims. Examine code coverage, make coverage, review quality metrics. So I'm a learner, so let's do the make on this to see it in action. So right now I've got my personal website here open. So we will go to my E drive, and then we will go to PowerShell, and then we'll go to we'll do bash cd nte, and I should have pulled it down to here. I thought, um, what was it? Well, I thought I put it down to there. Perhaps not. Perhaps not. Oh, there it is. Yeah, cd sovereign. There we go. Now I can open VS Code here. There we go. Okay, so let's do the make command um, here. Okay, so we're going to do make chapter one, or actually, I think it has to be under examples. Oh, and I hate it when this happens. Sometimes I'll accidentally take one keystroke that takes me 10 minutes to figure out what I actually did. Okay, so we're gonna run chapter one to see it in action. So probably in examples, and then oh, none of them say. Oh yeah, chapter one intro. Okay, source. Nope. Maybe tests. Nope. Um, Well, I don't see anything that says make run chapter one. Let's try entering it and see if it works. Oh, it does. Okay, so I think maybe this is something in the make file. Let's see. Yeah, okay. So it's part of the make file. Perfect. All right. So the Noah GIF style, and this I've talked about Noah GIF a lot on this channel. I'm really this everything he says here is gonna I'm gonna be agreeing with. So this book follows the code patterns from Noah GIF's repositories. Code demonstrates reality, not marketing speak. Benchmark every performance claim with statistical rigor. Show failures. Uh, so go and see. I think this is another, yeah, Japanese word for go and see for yourself. Yeah, yeah, yeah. Zero vaporware. Delete coming soon. Show working code. Master only Git. Oh, this is interesting. No feature branches. Push working code frequently. That's interesting. Okay. Um, Quality standards. This book enforces extreme test-driven development standards. 95% plus coverage enforced by PMAT. I'm not sure what PMAT is. Um, PMAT. Oh, well, it's not that. um, oh, here's the wiki says there's things. Uh, Not yeah, I'm not sure what PMAT means here. TDG, and this is what was it? Total. I forget. Grade greater than or equal to an A minus, 90 plus score, zero compiler warnings, Clippy-D warnings, 80% plus mutation score. Tests actually catch bugs. All examples compile and run. CI/CD validates. So I probably will be contributing. So found an issue, example doesn't work. We can file an issue here. Let's see if these got any open issues. No open issues, so I might be the first one. Include the chapter number, error message, and environment. So we have to include the version. Let's do that now, just to make sure that command goes through. There we go. So I've got 1.880 expected, and then include what you. So we fix it. Reproducibility is our promise. Acknowledgements. Okay, we don't have to read the acknowledgements. We don't have to read everything. So let's begin. Ready to see it in action? Yeah, so your first sovereign AI program runs in local mode with zero network calls. Welcome to the sovereign AI stack. Code is the way. So let's do it like this. We're going to run this again, and we just saw it run up there. So finished running it there. Hello, sovereign. So it created a local tensor so the computation results are here. Sovereign AI principles demonstrated zero network calls, full data control yeah. See. It's sovereign, right? This is running on my local system here. So I didn't call out to use an API, anything like that. All the data is mine. Doesn't belong to a big company that could potentially use it for things that aren't aligned with my own personal interests, transparent operations, deterministic rules, uh, EU AI Act compliance, data minimization, transparency, local processing. So this is perfect. This is going to be a way that I will run my models that I have as a result of that I can do on my 2060, but then I'll have as the 3090. And then when money isn't so tight, I'll be able to be able to upgrade even more and run more sophisticated models. and I'll be doing it. I'll be one of the only people in the United States running it in a way that's compliant with EU regulations. So I won't be having a model goading me into suicide or doing other really nefarious things. Is the idea. The model will be better aligned to my interests. Is the idea? We'll see whether that's the case or not. But that's it for the introduction. Stay tuned for more videos. We're going to start chapter 1 next.